My name is Mario-Cesar Suarez. I'm working at the Mexican Geothermal Association, and I am a member of the International Geothermal Association, working on geothermal reservoir engineering. I'm going to present a equation of state of water, the last version, programmed in Mathematica. I work for the Mexican Geothermal Association, which is a branch of the International Geothermal Association, and I'm very involved on geothermal reservoir engineering. I'm going to present you one of the most advanced equation of state for water at the present time. Well, together with air, water is the most important substance existing on Earth, for not only for living organisms, but also in science and in many industrial applications, in computational fluid dynamics, steam turbines, in high-pressure devices, and in supercritical systems. The International Association for the Properties of Water and Steam, it's an international association formed by several national committees in Europe, United States, Australia, Japan, Russia, and so on. This is the first version published in 1995, and I'm going to present you the last release of 2016. This formulation is a worldwide accepted mathematical formulation reproducing with maximum accuracy millions of experimental data obtained since the time of Carnot up to present time. And this formulation is presented here in the form of a computable notebook in the Wolfram programming language of Mathematica version 11.2. Okay, the water properties in this formulation are calculated for single phase, water and steam, and as function of density and absolute temperature, and for two-phase water, liquid and steam coexisting as a function of saturation temperature, pressure of saturation, of course. All water properties are defined in terms of the Helmholtz potential, that is defined as the energy, internal energy of the water, minus the product absolute temperature by entropy. And these are the definitions of every property important in water. This is pressure, energy, enthalpy, entropy, isochoric specific heat, isobaric specific heat, water compressibility, Joule-Thomson coefficient, speed of sound, and thermal expansivity. And as a result of this, we can define the thermal diffusivity of water. The units of these properties are indicated here. The Helmholtz free energy is in kilojoules per kilogram, density is in kilograms per cubic meter, temperature in Kelvin, pressure in megapascals, internal energy in kilojoule per kilogram, enthalpy kilojoule per kilogram, entropy kilojoule per kilogram, isochoric heat, joule per kilogram per Kelvin, isobaric heat, the same, compressibility, the inverse of Pascal, Joule coefficient is Kelvin divided by bar, speed of sound in meters per second, thermal expansivity in inverse of Kelvin, and thermal diffusivity in square meters per second. Surface tension of water is only needed for two-phase, can only be defined for two-phase water. Well, in natural systems like aquifers, hydrocarbon, and geothermal systems in general, as well as in atmospheric ocean interactions, water, of course, is the most important acting fluid. In particular, water in geothermal reservoirs covers a wide thermodynamic range because the temperature gradient between the core of the Earth and the surface produces a continuous flow of natural heat with different gradient of temperatures. This is different for shallow depths to medium depths, thousands of meters, and even to deeper depths, thousands of 10,000 or more meters, until the immense temperatures of molten rocks, that is around 800 degrees C or more than 1,000 degrees C. The normal thermal gradient on Earth is about average 25 degrees C per kilometer, but in anomalous thermal gradients like geysers or New Zealand fields or Mexican fields, the average gradient is about 150 degrees C per kilometer. And the wide range of temperatures for geothermal purposes is between 370 degrees C up to 5,000 degrees C. This is the core temperature of the Earth. And this depth go from 3 kilometers down to 6,000 kilometers, that corresponds to the center of the Earth. At the same time, in every anomalous zone, from a geothermal point of view, there is heat conduction flow and convection at the same time. And this is illustrated in the figure to the right. Therefore, water can be found in geothermal conditions at very, very varied temperatures and different conditions. Well, it's very important to see how is this, the molecular structure of water, because it's apparently a common substance, but we don't have intuition for these high pressures and high temperature conditions for geothermal systems. We only know water in the shower or ice or boiling coffee or something like that, right? Okay, I just want to explain you briefly that the molecule of water is composed by 2 hydrogen atoms and 1 oxygen atom, as everybody knows. But this molecule has a particularity that forms, the 3 atoms, forms approximately an angle 104.5 degrees. And the one very important point is that each hydrogen atom is in line between the oxygen atom of its own molecule and the oxygen atom of a different molecule in the neighborhood. So this is the figure illustrating this molecular structure of water. And this means, from a molecular point of view, that these hydrogen bonds have extra attractive energy, giving to the molecule of water an extraordinary stability that explain many of the unusual properties of water at different thermodynamic conditions. For example, water has large heat of vaporization. It expands upon freezing. It has low thermal conductivity in liquid conditions, but it has higher specific heat. That means it is capable of absorb and store a lot of energy, a lot of heat. At the same time, it has very low liquid compressibility, and at the same time, in the steam phase, has a very high compressibility. Water is basic and acid at the same time, and its index, pK index, is exactly the same, 15.74 for acid and for basic conditions. At the same time, water is a universal solvent, and water reaches its maximum density at 4 degrees C, not at 0, but at 4 degrees C. And below 4 degrees C, water density declines, and that is why, fortunately, ice floats on liquid water. I can show you this graphic showing these particularities. This is the water density at 1 bar pressure, and you see that exactly at 4 degrees C, it attains its maximum. After this temperature, the density of water declines. As I said before, all this is explained by the extraordinary stability of its molecule. Okay, now let's talk about this formulation. It's called 95 because it was the first version of the formulation. And this fundamental potential is the reduced specific Helmholtz free energy that is defined as the energy of water, internal energy, minus temperature multiplied by entropy. From this formulation and from this free energy, it can be reduced, make it dimensionless, just by dividing by R, the gas constant, and the absolute temperature. And this is called phi. Phi is function of delta, is the dimensionless density, and tau is the inverse of the dimensionless temperature. They are defined below. And this reduced specific Helmholtz free energy is formed by 2 parts. Phi 0, there is the ideal part, and phi r is the residual part, both functions of the same variables. This is very important to take into account because at the same time that makes it very powerful, at the same time produces some practical problems in a real geothermal field, as I will explain later. These are the definitions of the dimensionless density, is the normal density divided by the critical density, the inverse of the temperature, similar, and the reduced pressure, normal pressure divided by the critical pressure, defined here, the values are here defined. Now, if I write this formulations using the Mathematica code, it looks like this. Just take into account that they are very simple. These formulas were obtained by interpolation and very sophisticated nonlinear least squares. So the final formulas are not so difficult. They not involve any kind of special function. They are just logarithms, exponentials, and polynomials. That's all. All the n0, ni, c, b, so they are constants, they are coefficients, responsibles of the good approximation of the interpolation of the nonlinear radial, least squares. Of course, I cannot include here the coefficients because there are too many, but they are programmed in apart. Besides these two definitions of the main phi0 and phi parts of the Helmholtz reduced energy, we need the derivatives of these functions that were also obtained in a coherent way by interpolation and least squares formulas. And we need all these things, and all that you see here on the screen is the formulation of the international properties for water and steam. Okay, now I have to want to present you the 4 phases of water in this formulation, including ice. Ice, liquid, steam, and supercritical conditions. You can see it in the figure. The figure shows here to the left is the solid. There are several subregions, including I6, etc., included in the formulation. I don't use it. I just start from 1 or 10 degrees C. The triple point of water is included: steam, liquid, and gas. Solid, liquid, and gas. Sorry. And up to the left is liquid phase. Here, this curve is the two-phase conditions where temperature and pressure are not independent, but they depend each one of each other. That is called the saturation conditions and the critical point of water. Below this critical point to the right and up to this point, there are the supercritical phase of water. Let me tell you something about the limits of the formulation. For density, for pressure, sorry, it goes from very low pressures, so 0.1 or 0.01 bar, up to 10,000 bar. And for temperatures between 0 degrees C and 1,000 degrees C. But it can be extrapolated up to 1 million bar and almost 5,000 degrees, 5,000 Kelvin. These are the ranges that the water can be calculated using this formulation, but they are not experimental range, they are only extrapolations. And you will see in some graphics later why it is so like that. Okay, these are the functions defined in terms now of the Helmholtz potential and its respective derivatives. It's pressure, internal energy, specific enthalpy, specific entropy, isochoric heat, isobaric heat, bulk modulus, isothermal compressibility, and thermal compressibility and thermal conductivity, speed of sound at the end. Well, here I have to tell you that the blue lines mean the extended version of this formulation that I did it myself, just using the same formulas, the same derivatives, to include these properties of water. There's just analytical calculations and obtain a closed formula for these properties. I have to explain this thing. In practical terms, all functions and derivatives are computed as functions of delta and tau, density and inverse temperature in this formulation. But in geothermal fields, it's very difficult, if not almost impossible, to measure the density of water with the required accuracy, because this formulation is so precise that we need at least 6 figures after the decimal point to compute with this thing. Therefore, we need to inverse the properties to calculate first density and then with pressure and temperature, and then use it to compute the final properties. Well, it's very, very, very rare or strange that the best thing to use with this backward formulation is Newton-Raphson classical technique. I didn't find nothing better than this one. The error here is almost 0 very often, up to 10 to the 9, 10 to the minus 10. and the convergence is attained in 2 or 3 iterations maximum. This is the formula of Newton-Raphson here in the first formula in terms of the IAPWS formulation. And at the end, I obtain an approximated value, but very close to the real value of the density, and then I can use it again into the original formulation. All these things were formulated and programmed within a module in a single cell, computable cell in Mathematica 11.2 using the Wolfram language. To test the validity of this formulation, I used the same conditions, proposed by the association and are indicated here. Okay, if you compare with the original documents, you will see that these values obtained with Mathematica are exactly the same as the proposed figures to verify the code. So therefore, the code is verified, and we have a very nice formulation. Now let's explain you briefly how it works. The code works with the main module. I call it IAPWS-95, of course, in terms of density and temperature, and inside it becomes dimensionless by the definition I explained before. And the general program overview is as follows. First, I need to approximate the density with an old and more simple formulation. It's called the International Formulation 1967, because it was the year of the formulation. And the module itself, this is the body of the main code. Then I define both parts of the Helmholtz free energy, Phi0 and Phi-r, and their derivatives, the computation of single-phase thermodynamic properties, and the computation of two-phase thermodynamic properties, because they are doing differently. And final, a display of results in tabular or in graphical form. Okay, we can have a look at the code. Sorry, but this is in Spanish because I speak Spanish. Sorry, I will not have time to translate it. But just the first part is explaining what's happened, some backgrounds, some reference. And here, this part, this is for the density. The first part is for the density of liquid, and the second part is for the density of steam to approximate the density for the backward formulation inversion. Now, it starts here, the IAPWS 2016 code. The constants, all the parameters are defined here. And here starts the definition of the ideal part of the Helmholtz free energy. And its derivatives, I want to go very fast. Derivatives, and then more coefficients, more constants that I need to formulate the residual part. I need some auxiliary functions inside the code, and here are the more derivatives and so on. And this is the formulation of the residual part of the Helmholtz energy. Okay, everything's done. All the rest of the code is just to compute things and the derivatives. And here is the computation of the analytical formulas for the properties I said before. And finally, the presentation of results. There are several options I will show you now. Options are somewhere here. This is two-phase conditions, and this is the several options. And finally, graphics conditions or tabular form. Okay, let's have a look at how it works. I need this cell to introduce the program. Okay, now let's say I'm going to calculate one state only. This, how many states you want to compute? One. Then I have this properties of the program. For example, display program capabilities is option number -1, and it just gives me the properties that the program can calculate, and that I explained it before. I can have the opportunity to terminate here the program or to continue. I continue, and then, for example, I'm going to present some graphics. So I say thermodynamic 7. Option 7 is plot a given property in 2 dimensions or 3 dimensions. What kind of graphic, 2-dimensional or 3-dimensional? I choose 2-dimensional. And then which property? Well, I can choose one, pressure. And which can liquid or vapor? I choose vapor. And then for which temperature? Let's say, I don't know, 95. That's all. Finish. Oh, there's a problem here. I have graphic 2. G2 is for 2 dimensions. G3 is for 3 dimensions. Let's see what's happened with the 2-dimensional graphic. Oh, sorry, it didn't work. Okay, let me do it again. I don't know what's happened with the product. I just tested before. We make a 3-dimensional graphics. 1 again. 7. 3D. And pressure again. Temperature, you can see for liquid, let's say 95. Okay. Now G3. Oh my God, something is wrong. Sorry. When I tested the program, it worked fine. Okay, let me show you another thing. Let's compute now, for example, 3 states. 3 states. And I will show you how it works with backward liquid phase thermodynamics. It's option number 3. Okay, one temperature, 1 bar. This is a generated table. Then I really don't know what's happened with it. I will show you the previous graphics I made. For example, this table is for liquid conditions, and it's presented in tabular form for all the conditions I said before. This is liquid. This is mixed. Some parts are for liquid, some parts are for steam. And these other tables are to verify the properties. The first table is exactly with the density and temperature conditions required by the Helmholtz free energy. And the second table is for the backward formulation, inverse formulation. And you can see that there are very, very small differences between both tables for density and for pressure and for the rest of all the other conditions. This is for a supercritical region and steam. You can see that we can go from 100 degrees C down to 4,000 degrees C and 10,000 bar. And all the conditions are here. I just want to show you one very important thing concerning density of water. If we are talking about steam, for example, at these conditions, we have a very low density. It's vapor, it's steam, 0.59 kilograms per cubic meter. Okay, if we go down to 400 degrees C and 250 bar, we are on supercritical conditions. We see that we have 166 kilograms per cubic meter. So as long as the energy of steam depends on its density, that means that when producing electricity using steam in supercritical conditions, it's much more efficient and it has more heat available to generate electricity. Unfortunately, the turbines to use supercritical steam, they are not ready. It's just a question of technology to use it. But the normal geothermal steam used now is for 250, 300 degrees C, 350 degrees C, and not more. The future for geothermal energy is in the supercritical phase. Okay. The other table shows the same, the approximation I made with the free. And this is a very nice graphic because it shows the whole thing. The red ball is the critical point. This is the two-phase region, all this, two-phase zone. Here to the left is liquid, and to the right is steam. And up to this ball is the supercritical conditions, the supercritical region. Of course, I have to cut this because it extends very, very far. And this is only up to 800 degrees C. I have more. What's happened in the supercritical region? This, and as I say, maybe vertical is better. You see, after the critical point, the behavior of pressure as function of enthalpy becomes almost straight lines. That is why it's very good to extrapolate the formulation for the supercritical region. The behavior is very simple, more simple than close to critical point. Other properties are the dynamic viscosity, density of water, specific entropy. And now the last, this is entropy again. One important thing concerning the powerful of this formulation. It's very good, but it's not perfect. You can see in this graphic, this is a graphic show the dependence of specific isobaric heat with temperature, and something strange happens around the critical point, okay? It behaves like the values are too high. If I compare with other pressures, yes, I observe this. After the critical point, the behavior becomes more stable. And if you see it in 3 dimensions, we can calculate one of the formulas appearing in the calculation of the specific heat. And of course, look at here, I have to divide between 10 to the 15 to visualize this behavior. And if I reduce the range of the same formula, the same part of the CP calculation, I observe I have 2 singularities. And the region is 1.98, 2.1, very small. It's a typical behavior of singularity. And this is a problem with a mathematical formula, but it cannot be solved just by arranging things. No, the solution is experimental solution. And this is the 3-dimensional graphics of the specific isobaric heat. So you can see that it's a singularity appearing around the critical point. And something similar happens with isothermal compressibility. Well, okay, that's all. I just come to end my conclusions. Okay, the conclusions are, okay. Thank you very much.